Okay, for this early career researcher seminar at CASI, we have Junsup Shim from KIAS, who was previously a PhD student at SNU, and he's giving us a talk about clustering of critical points in the evolution of the cosmic web. Junsup, go ahead.
Okay, thank you, Christoph. Hi, everyone. I'm Junsup Shim from KIAS, and thanks to organizers for having me in this ECR seminar. Today, I will talk about clustering properties of critical points and their redshift evolution. This work has been done with collaborators in different continents, Sandrine, Christoph, Dimitri, and Konta. So why do we care about clustering properties? The clustering properties have been the major source for cosmological studies because the underlying physics governing the evolution of the universe highly impacts on the clustering properties. And here, the underlying physics means new ingredients in the various cosmological models, and could be meaning different nature of dark energy or the gravitational law, which are deviating from the general relativity at large scales, and which can also include some amount of non-Gaussianity in the primordial fluctuations. And to actually measure the clustering properties, galaxies and galaxy clusters were most frequently adopted as tracers, and quasars for high redshift, and even for more higher redshift, CMBs also has been adopted. And recently, there are a number of papers using cosmic voids to study the clustering properties. So why are we trying to add critical points in addition to these traditional tracers? These critical points are a means of compressing the relevant information of the underlying field, in our case, the density field. For instance, for a given initial density field, the topology of that field is encoded in the position and the height of these critical points. And these critical points are not just imaginary, meaningless locations in the density field, but they are likely to be the formation sites for physical structures. For example, massive clusters are known to form at the high enough peaks of the initial density field, whereas cosmic voids will form at the low enough trough in the density field. Likewise, large-scale filaments or slow-on great wall like sheet structures will probably anchored to the filament type or wall type saddle points. So these critical points are, and the lines joining these points are the backbones of the cosmic web. So studying the clustering properties of critical points will not only make you learn about the initial topology of the density field, but also will let you learn about the clustering properties of such large-scale structures. So how do you actually define critical points? It is a point where the gradient of the density field vanishes, and there are 4 different types of critical points based on the signs of the eigenvalues of the density Hessian. And these eigenvalues gives you some sense about the behavior of the densities around each critical point. For instance, if you think about a peak point in the density field, their eigenvalues are all negative, meaning that in all 3 principal directions, the density is decreasing. And the opposite is true for void type critical points, where you have all increasing densities in three principal directions. And when you think of filament type of saddle points, then you have one positive and two negative eigenvalues, which lets you know that in the direction corresponding to lambda 3 is the direction where the density is increasing the most rapidly. So you can have analogous explanation also for the walls. So the final goal of this research is to investigate the clustering properties of critical points through measuring the auto and cross correlation functions of these critical points. So to identify critical points and measure the clustering properties, we use about 500 realizations of vanilla lambda CDM cosmology. And before we go further on, I would like to briefly mention the relevance between critical points in our setup to physical large-scale structures. So we adopted 6 H-inverse megaparsec Gaussian smoothing filter. And this crudely translates into the mass scale of 10 to the 15 H-inverse solar mass. And having said that, the highest 5% peak type critical points at redshift 0 can be associated with collapsed halos of that mass scale, considering the heights of the 5 highest peaks compared to the RMS fluctuation of the field. So you can extend this idea to other types of critical points. So different types of critical points, for instance, wall types or filament types or void types are proxies of the large-scale structures of the same kind at that mass scale. And these critical points at the higher redshifts are likely to be tracking the progenitors of these structures. So now I will give you the one-point statistics of the critical points. Here the x-axis is the rarity nu, which is defined to be density contrast divided by the RMS fluctuation of the field. And the y-axis gives you the relative fraction of respective critical points, respective types of critical points. And there are multiple lines colored with different colors depending on the types of critical points. So now let's first focus on dashed lines, which is the theoretical prediction from Gaussian random field, having the same power spectrum. So if you look at, first look at this blue filament, blue lines representing filament distribution and wall type critical point distribution, you clearly detect a symmetric feature about nu equals 0. And there is another symmetry between void type critical points and peak type critical points about nu equals 0. So it is easily understood because these void types and peak types are just equally likely draws from the Gaussian random field, except that the physical conditions on the density or the eigenvalues are just the sign opposites. So that is why we are having symmetric feature about 0. And this is also true for filaments and walls. And then if we let them evolve under the gravitational evolution, Now, this solid lines represents time evolution of the density distribution of critical points. Now you can see that the final shapes are a lot different from the Gaussian random field of predictions, meaning that it lost its initial information at the end, and also the symmetry which existed in the initial conditions are now totally broken. So in terms of one-point statistics, the symmetry in the Gaussian random field is totally broken even at this mildly nonlinear regime. So now we're going to use these critical points to measure the 10 types of correlation functions, and 4 being autocorrelation functions with critical points of the same type, and 6 cross-correlation functions having different types of critical points. And 4 of them are mixing different sign densities of critical points, and rest of the 2 are pairing same sign densities. So I will explain in more detail in the next slide about this idea. So we are actually extracting a specific population of critical points among its kind. So for instance, for peaks and filaments, we are extracting the most overdense 5% to 20% peaks among their whole population, whereas we pick out only the most underdense 5 to 20% walls and voids. So peaks and filaments are sitting at the extreme overdense range, whereas walls and void type critical points are sitting at the opposite underdense range. So using these specific populations of critical points, we now see how the clustering properties of these points change as a function of rarity. So I will first show you how the autocorrelations of critical points change. But before we interpret the results, let us briefly recall what correlation actually tells you. So the correlation function provides the information of the clustering strength of tracers of interest at a given scale relative to the random point distributions. So in other words, correlation function is an excess probability of finding such pairs at that given scale compared to the random point distribution. So in our plots, I'm plotting 1 plus psi, which means 1 plus correlation function. So if it is above unity, it means they are more clustered compared to the random distribution cases. Whereas if they are below the unity line, then it is the clustering is weaker than the random distribution. So to measure the correlation function, we adopted a modified version of Davis and Peebles estimator. And we analyzed small to intermediate and finally to large scales. And we'll now first focus on the small to intermediate separation. And here there are 4 types of autocorrelations pairing same types of critical points. And each of them have been measured using different subsamples with different rarity. So here 5% means the rarest 5% population, and they are 5% the most overdense peaks. And for walls and voids, here 5% is applied on the other side of the density range. So they are most underdense 5% of population among them. So as you can see, the transparent line lies at the top in all cases. And if you increase, so if you go for less rarer events, you have weaker clustering. So it means for rarer critical points, the clustering is enhanced, meaning they are more clustered. And it can be understood in terms of linear bias of critical points with respect to the linear dark matter correlation function. Here, the linear bias is proportional to the square of the height of the critical points. And this height is higher for rarer critical points. So in the end, rarer critical points are more biased tracers of the density field, which is reflecting the well-known effect of biased tracers being more clustered. And there's many classes of vertical lines, and these vertical lines are indicating the position where the maximum correlation is happening for different abundances. And you can see that as we go for rarer critical points, this vertical line is moving to smaller separations and consequently yielding narrower anti-clustering region. And this is because the height difference or their density difference between two critical points are smaller for rarer critical points. And that leads to slightly, so these kind of points are more likely to be closely separated. So the peak of the correlation is moving inward. And it is really astonishing to tell that these measurement at redshift 0 is almost perfectly consistent with the predictions from the Gaussian random field. So you can regard this prediction is coming from the initial density field. And you can see that the general amplitude as well as the position of the maximum correlation occurs are almost identical. So it tells you that the initial information of the density field is kind of preserved even at this mildly nonlinear regime if you use clustering of these critical points. So if you move on to large separations where BAO features exist, so there's a vertical line indicating the position of the BAO bump inferred from the linear dark matter correlation function. And here the dashed line represents the linear dark matter correlation function multiplied by a factor of 8 in order to match the overall amplitude of the measured correlation functions. So this then naturally gives you the sense that these measured correlation functions at BAO scale, the BAO feature is enhanced because these dashed line is the amplified version of the linear dark matter correlation function. And you see that there are stronger rarity dependence compared to the bottom two cases there is a larger deviation from profiles to profiles, meaning that these overdense critical points, peak, and filaments are more susceptible to nonlinear gravitational evolution, whereas these underdense pairs of critical points are relatively free from these nonlinear evolution. Now we are moving on to first type of cross correlations, and it is pairing overdense critical points with underdense critical points. And as you can see, the general shape is totally different from what we have seen in the autocorrelations. First, we note that the clustering amplitude is below unity, which means these pairs are all anti-clustered at all scales. And there's even some extreme region called exclusion zone, where you won't be able to find any pairs below this vertical separations or vertical scales. And thirdly, there is a monotonic increase without presenting any maximum in the correlation. So this is a major feature we can observe from the first type of cross correlations. And their dependence on rarity is a kind of opposite to the autocorrelations, in a sense that the transparent line for 5%, which means we are using most rarest critical points. So these peaks are the most highest ones, and whereas these wall points are most underdense ones. So their clustering is weakest compared to the others. And this is because the density difference between these two critical points, say peaks are at the very highest end, and the walls are sitting at the very lowest end. So they are more separated. So that's reflected in the correlation function, having a small number of pairs at given separations. And this logic also applies to the rest of the correlations. And you can also observe the size of the exclusion zone, which is represented in vertical lines, are moving outward for rarer critical points. So this is again due to the relative height difference between the 2 points. So if the height difference between the two critical points are larger, then the size of the exclusion zone is getting larger. And what is interesting here is that the BAO feature is now represented in a different shape. So in autocorrelation functions, we usually had bumps, but in this case, it is now represented as a dip. And this is showing you that at this typical BAO scale, the anti-clustering is more enhanced in this case. So this is an interesting feature, which is represented as the opposite way as we usually see. And finally, this is the second type of cross correlations, pairing overdense peaks to overdense filaments, and underdense walls to underdense voids. And again, now you have totally a new picture. You have a divergent feature at very small separation, although it's truncated. And you have local maximum at some scale. And as you can see, there is also a similar trend in terms of rarity dependence. So the clustering is more stronger for rarer critical points, which is due to the linear bias of these critical points. And if, again, we look at BAO scale, now we turn back to BAO bump because we are pairing overdense to overdense and underdense to underdense critical points. So we are having effectively positively biased correlation functions. So BAOs appearing as a bump. And again, we are looking at a stronger rarity dependence compared to the bottom panel, which is again due to the nonlinear evolution, gravitational evolution in the overdense regions. So, so far we have studied how the correlation function changed as a function of rarity, and now we will see their redshift evolution. In this case, now we are fixing the rarity of the critical points. So for instance, we are extracting only 20% highest peaks in filaments and 20% lowest, the most 20% lowest walls and voids. And as you can clearly see, there is no significant redshift evolution at small scale. And it is also half true even at the large scale, but you see some evolution in the peak and filament autocorrelations. And this is supporting our previous argument that the BAO feature is broadening and its peak is moving inward as time goes by. And this supports the idea that they are evolving under, suffering from the nonlinear gravitational evolution. And on the contrary, wall types and void types are relatively stable in terms of BAO position. Now, if we move on to first type of cross correlations, we are very sure that we see negligible redshift evolution at all scales. And also we see very stable BAO position as a function of time, except filament wall cases. And finally, if we look at cross correlations between peak filament and wall void, now you see some redshift evolution. So for peak filament case, the local maximum grows higher, meaning that the clustering is becoming more stronger, meaning they are mutually attracting each other. So they are more clustered at these scales. Whereas the local maximum in the wall void case, they are decaying, meaning that the clustering is becoming weaker, again, meaning they are more uniformly distributed at all scales by pushing each other as time goes on. And for the BAO scale, you again see a stable BAO position only for the case of underdense pairs. So, so far we have focused on distance scale between different types or same types of critical points. And then you may wonder how these critical points are spatially organized in our universe and its relevance to physical structures. So to answer this question, we now search for some preferential direction where the clustering is the strongest. So we actually measure the anisotropic contribution to the cross correlations. So as an example here, I'm showing you a peak filament case. This is the previous total cross correlation function previously we had seen. And we have divided angular contributions coming from different angular bins. And this angle is measured with respect to the eigen direction corresponding to this lambda 3. And this lambda 3 is the direction of the density increasing most rapidly. And in other words, this is also the direction of the large-scale filamentary structures. So, so the most transparent pairs, the contribution coming from the pairs perpendicular to this direction and parallel to this direction. So you can see that the whole configuration is majorly captured by the most opaque line, which is coming from the parallel direction to the filament. And it is telling you that most of the peak and filament pairs are found in the direction along the filamentary structures. So I will skip rest of the two cases, but you can also extend this analogy to the rest of the cases. And for the case of walls and voids, you can also do a similar analysis. Now, in this case, we are measuring angles with respect to the eigen direction corresponding to lambda 1, which is the direction of the density decreasing most rapidly. And again, you can see that the characteristic feature of the total wall void cross correlation is dominantly captured by the most opaque line, which is the direction, which is coming from the direction along this direction. And crudely speaking, this is the direction perpendicular to the sheet-like structures. So I was mentioning very complicated directions and structures in a complicated way. So I will give you the visualization. So these figures are showing you the 3D number excess of extrema points around saddle points in the frame of saddle. So for instance, on your left, there is peak number counts around saddle points, which are filament saddle point, which is sitting at the center of this sphere. And we are projecting this distribution onto respective planes. So as you can see, there is a vertical concentration of peaks along this direction. And this direction is corresponding to lambda 3. Again, this is the direction where the density is increasing the most rapidly. And similarly, if you look at voids, void type critical points around walls, there is a horizontal concentration, meaning that it is highly likely to find voids in that direction. And this is again the direction perpendicular to the sheet-like structures. So so far we have been we have been dealing with most overdense peaks and filament and most underdense walls and voids. And if we think of real physical structures, for example, a Sloan Great Wall, these are actually sheet-like structures which probably will be anchored to wall-type saddle points, but they are overdense structures. So in that sense, our constraints previously we used are less likely to be physical. So we changed our limitation in the density range of walls and voids. So we now use most overdense wall points and void points. Then you may ask why we are using most overdense void points, and may wonder if there exist overdense void points. But if you recall the earlier slide, which I showed you, 1-point statistics, even voids at late time, there is a very small population of void type critical points which are overdense. And these critical points can be understood as a faint void surrounded by prominent overdense wall-like structures. So we are doing similar analysis by computing cross correlations for peak filament and peak wall, peak void. But in this time, filaments and walls and voids are all most overdense populations. And if you compare this to the previous ones, which we restricted to most underdense walls and voids, they are no longer anti-clustered, but they rise above a unity line. And they also represent some maximum in the correlation. So you can then measure these maximum, the radii where the maximum correlation occurs. And it seems that these specific scales are less likely to evolve with respect to time. And if you compare these configuration to the theoretical prediction from Gaussian random fields, you confirm that these features are already encoded in the initial stage and persist even to the late time. So then you can simply compute these distance ratios, which is 0.7 and 0.6. And these values suggests us that these critical points are spatially organized in a form of cosmic crystal structure. So for instance, peaks are located at the center of a cube, and filaments sitting at the center of faces, and wall points are in the middle of edges, and void points are located at the vertices. Then you can simply compute the distance ratios between these different distances, and it gives you 0.7 and 0.58, which is remarkably close to the values obtained from the measurements. So in that sense, we can statistically say that the spatial organization of these critical structures can be captured in terms of cosmic crystal. So combining all these findings and what can we do? So I am currently working on using these features in the clustering as standard rulers. In particular, as you have seen, there are particular scales like the size of the exclusion zone or the radius where the maximum correlation occurs. And you also notice that these scales are quite insensitive to the redshift evolution. So it gives us some clue that we can use these as standard rulers. So I'm working on that. And another direction is to actually measure these clustering properties using the observational data, like using emission line galaxies or luminous red galaxies from DESI, or you can also use Lyman alpha forest or quasars for in higher redshifts. And actually, one of our colleagues are working on giving a forecast on the quality of these measurements using Weave QSO survey. And finally, we can also apply these strategy to critical points in 2D, which can be applied to the H1 intensity mapping or weak lensing convergence maps, so that we can dig out some complementary information. So I will summarize. So from clustering properties, especially two-point correlation functions of critical points, we found many interesting features. But to pick out most interesting ones, there exist some special clustering scales in these correlations, and the BAO feature is amplified compared to the linear dark matter case, and in some cases, their position is quite robust across redshift, which may be advantageous to be used as standard rulers. And also, we had some idea on how these critical points are spatially organized, and we can say they are in the picture of a cosmic crystal in a statistical sense. So I'm looking forward to using these critical points as a cosmological probe. Thank you for listening. I will stop here. Thank you.
Thank you very much, Junsup. Any questions? Okay, that's applause again. So if you have any questions, just raise your hand in Zoom. And yeah. Okay, if there are no questions. Oh, there's one from David. Please.
Oh, Benjamin has a question as well. I have a really stupid question, I'm afraid. Can you go back to your figure which shows the correlations just a few slides back, just before your crystal?
Okay, this one probably.
Okay, so there you have the 1 plus the correlation function for the exactly. You have 1 plus the correlation function for the filaments, walls, and voids.
Mm-hmm.
And you're comparing it with the Gaussian prediction.
Yes.
So I didn't quite understand this because you still, in order to generate, I mean, if I have a truly Gaussian random field with random phases,
mm-hmm.
why would I have walls, filaments, and voids, right? These things are kind of generated by phase correlations in the structure. So I'm not sure I understand how you made your theoretical prediction there, I'm afraid. Could you explain a little bit more?
So, the measurements coming from the theoretical prediction is not generating actual Gaussian random field, but it's coming from by computing the conditional probability by constraining the critical point conditions. Okay. So we're not actually measuring in the initial state. It's just a purely theoretical computation, analytic computation. Yeah.
Okay. Okay. So sorry, that was so like I think my brain just did a freeze, and I was like,
No,
anyway.
I think I forgot to mention that it was coming from pure analytic. Predictions. Sorry about
that's
that.
great. Thank you. Thanks very much.
Okay, the next question is from Benjamin. Please go ahead.
Yeah, great talk, by the way. I really enjoyed it, and it's really cool stuff. Yeah, so you mentioned the possibility of using it as ruler, basically. Can you? So first, which or which typical size do you want to use as a standard ruler?
Okay, for instance, in this plot, you can see these vertical lines, and this is the size of a so-called exclusion zone, below which you won't be able to find any pairs. So it's a kind of region where finding these pairs of critical points are suppressed. And this is actually already encoded in the initial conditions. And this is only a function of smoothing scale. And as you have seen, there is no redshift evolution. So given, suppose we have a given power spectrum initially, then we are able to calculate this specific size of the exclusion zone at every redshift, because it's not actually evolving. And then you can measure in observation using assuming some cosmological model, then you will be able to constrain the equation of state of dark energy. That is our guess, and we are working on in that direction.
Right. So then, to understand how depends on your cosmology. Say you've the, I don't know, omega matter or whatever, it will probably not much, a little bit. So
also you're talking about cosmological parameter dependence, right?
Well, yeah, because it's mentioned that you want to use it to constrain the cosmological parameter, right? So, the thing is here in your simulations, you fix the cosmology. So you, I think one next to look at the dependence, and I expect it depend too much because we parameter. So as long as you don't depart too much from.
So yeah, that's a good point. So previously, I briefly worked on to seek if there is any cosmological parameter dependence. So using multiverse simulations, as you are already familiar with, we have also did similar analysis measuring the correlation functions. And then there are a number of different cosmologies. And I'm not sure you can clearly see the differences between them, but overall, there is a very small effect coming from the different amount of matter or even dark energy. It's only a matter of evolution, I guess. So even for different cosmologies, these particular scale does not change much, which means they are relatively insensitive to the change of cosmology. So we can single out the effect is only coming from the assuming wrong cosmology instead of the
nice.
its original dependence.
Okay, thank you very much. The next question is from Buyo.
Oh, hello. Yeah, thank you for the great talk. Your plots look amazing.
Thank you.
I was just curious about more like practical side of this classification of different critical points.
Yes.
So these are all like this classification is done by computing the Hessian matrix and looking at the signs of the eigenvalues. Is that correct?
Yes. Yes.
So yeah, so I can imagine that like some of these numbers might be quite close to zero, and potentially you might have like a very smooth Gaussian field where like, there's a tiny bit of fluctuations, and it, although it's nearly constant, some points might accidentally become classified as voids and stuff. So I was wondering how these kind of noise effects are dealt with in the
Okay,
both in
so
experiments.
yeah. So that's actually a good question. So it's related to, I guess it's related to the problem of the size of the filtering scale. So if you are to apply very small smoothing scale, then there will be very many peaks and voids and walls or saddles. And considering our simulation resolution, and we decided to use 6 megaparsec, which encloses about 3 pixels. And this is, we concluded that this smoothing scale is safe enough to securely identify these critical points. So if you would like to apply these idea to actual observational data, you must also consider how well the tracer density field reproduces the underlying dark matter density field. That is one thing, and then you have to choose again a appropriate scale of smoothing length. So that will make your contaminations as low as possible.
Right, thank you. That makes a lot of sense.
Thank you.
Okay, the next question is from Jong-in. Please go ahead.
Hi, thank you for your nice talk. And I have a really simple question about the autocorrelation function that you showed.
Okay.
I can see the gray lines.
Okay.
Yeah,
Yeah. Yes, I forgot to mention because of the time limit. So actually, these colored lines are filtered version of the raw estimation, raw measurements. So, for instance, if you look at large scales, there are pretty much ugly wiggles, and we are smoothing these profiles to make it smoother. So that is why and the reason why we are showing these gray lines in a fainter color is to show you the characteristic variation around these filtered profiles.
So the gray lines are unsmoothed, the correlation function from the unsmoothed density field, and the colored lines are smoothed, the correlation function from the smoothed density field. That's right.
So both profiles are from smoothed density field.
Yeah.
But colored ones are smoothed version of the profiles. So they are you can understand in this way. So the gray lines are the original measurements from the smoothed density field.
Okay.
And then these profiles are so wiggly. We try to see their trend, and then we apply some filter on that profile to get rid of the wiggles.
Oh yeah. Oh, okay.
Yeah, sorry for the confusion. Yeah.
Okay, thank you. We have another question from Stephen now.
Hi, Junsup.
Hi.
Hi, thanks for the talks. Very good. I have a few questions, quick questions, hopefully.
Mm-hmm.
First of all, you use the Hessian to define the critical points.
Mm-hmm.
And you define them as being either positive or negative. But typically in the late universe, people don't actually use that. They because the density field is actually asymmetric, so they use the value of the eigenvalues above or below a certain, I think 0.5 or something. I think Benjamin's done work. So is that arbitrary? I mean, why do you select 0 as the limiting case here at low redshift?
Yes, so there isn't a specific reason for choosing 0 as the threshold, as you can. So I get your point. So if you, for instance, if you are trying to define some physical structures using density field, there are many approaches giving some positive or negative threshold to match the visual more closely to the visual impression of physical structures. But in our case, I think it's just we are starting from the pure analytic like a historical background. We're just simply assuming 0 to be the criteria, but maybe if that makes a big difference.
Maybe it wouldn't, because you're only looking at the rarest objects, right?
Yeah.
So in that case,
yeah, so the curvature will be more or less.
Yeah, I think it's worth checking, but yeah, it's probably not going to be important for you, maybe.
Okay.
So my other question is the rarest. You use the rarest objects, right? So they correspond to the largest filaments and the largest,
yes,
objects. And so I guess the reason why these are almost
redshift independent.
Yeah, redshift, because these large critical points don't really move very much, and they don't interact, and they don't. So, but as you decrease, so as you use increasingly less rare objects for your statistics, you'll get more statistics because you get more objects, but you're also increasingly losing the property that you want. So, have you explored varying sort of the rarest percentage of objects and seeing how that affects your statistics?
So we haven't go down far to like more than 20%, because if you so it is hard to display where a 20% is located in this plot, but if you go far from 20%, it starts to overlap with other types of critical points. So it is hard to disentangle the effect coming from same density. So we try to make it as simple as possible. So we constrain to the rarest populations. But as you can see, if you search for different ranges, you can make a zoo of different combinations, but we are not sure which one is close to physical interpretations. So we are starting from the most intuitive cases. But I think it's worth trying to search for the significance or the meaning of the different rarities.
Yeah, find the optimal case where you get the best statistics. Okay, thanks. I've got one last comment, really. So the crystal thing, that Christoph likes to talk about. Can you define, so you have a crystal composed of 4 distinct elements, and you have 2 ratios. So is that enough to specify that it's a crystal? Don't you need more?
Yeah, so that's I think that's a crucial question. So it's like proving, is this the only solution to this problem? But as far as I can think, it is for us, I think this is the most appropriate solution to this, because even in between peaks and filaments walls and voids, there has to be some order because of their eigenvalue conditions and their density conditions. So these peaks cannot directly meet walls or voids, and etc., etc. And combining all these constraints in our mind, we ended up having these cubic structure. But yeah, but it's hard to tell if this is the only unique solution to incorporate these distance ratios.
Okay. Okay, great. Thank you very much.
Thank you.
Thank you very much. Are there any more questions? If not, one brief question. You mentioned DESI as a possible application. Have you already run your algorithm or method on a more realistic model catalog? I think you were only doing box simulations so far.
Yeah, so I haven't yet applied to like mock catalogs, because we are in the stage of assessing the possibility of using this as a robust standard ruler. So I'm working on mock catalogs of Horizon Run 4 to see if the effect of assuming wrong cosmology, and then if we find a significant difference in the clustering properties, then the next stage will be naturally to apply this idea to real data. And that's,
okay. Thank you very much. I think we are essentially out of time. So, okay, let's thank the speaker again, and
thank you. Thank you for listening.